All right, next up we've got Dr. John Kevern to talk about penetrating sealers for concrete pavements. This is one that I think a lot of us are going to be interested in. I know in Indiana we've seen a lot of joint deterioration that we're blaming on our calcium on our de-icers, so I'm interested to see what you're going to tell us. Thanks.
All right, thanks much. So we are changing gears a little bit here. Everybody gets a gold star. As the students and the faculty tell me, 9 o'clock is a completely unreasonable time to do anything. And this whole room was here at 8 o'clock, so clearly it's a bunch of construction folks. So it's a good, good room. So even if we had a late night last night, we're still functional in the morning, right? So, okay, so I am, apparently didn't put my name on this. So I'm John Kevern. I am a professor of civil engineering at UMKC, and I'm the director of the division in the built environment there. So I've got about 11 programs under me. And so sealers is one of these things that we are, it's kind of the Wild West right now. And so if I go to the bridge preservation meetings, probably I'd say a third, at least a third, maybe half of the folks out in the exhibitor area are sealers, I'd say hawking wares of one flavor or another. And so what I'm going to talk about today, we've got real good research. I will show you some figures so you can check that box off for your reimbursement. But let's talk about honestly how these work and where we would apply them appropriately. So if we're going to spend the money, we are going to preserve our pavements. Let's just not waste our money here. And so acknowledgments here. So things I'm pulling from work from Iowa Highway Research Board and Wisconsin Highway Research Program and NCHRP projects. And we've got samples up at Min-Road right now on our anti-icer project, and work with the CP Tech Center and all the good stuff. And since we're in Missouri, I'll mention I got the MICTI logo here. So Missouri Center for Transportation Innovation is a joint center between all of the University of Missouri system and the Missouri Department of Transportation. So if you are in Missouri and you start seeing that logo, we meet with Bill Butler there at MU on the asphalt side every week, and John Myers down at Rolla, and George Sedition at UMSL. And so this is to increase the amount of research and the visibility of research here for Missouri. So, all right, so we look at concrete, and we can spend all day long talking about concrete deterioration. And if I start to look at there on the upper left, we have this kind of, we'll call joint rot. And so depending on where you're at and depending on what DOT and sort of what research study has been done there, there's a variety of reasons. So in the old-timey days, we would say, oh, that's a poor quality, poor freeze-thaw durable coarse aggregate, so that's decracking. That's a piece of it, but it's not all of it. And so I'll just kind of challenge you for the DOT folks, if you kind of go out and about, you've got a lot of pavements that are probably attributed, concrete pavements, to decracking, that once it cracks and sort of spalls out of there, then you'll cut out the joint, you'll replace that with fresh concrete, and it'll be fine. And I will say, if you did that, it's not decracking. You mucked it up during sawing or during construction. And so it's a fine quality. You just did it during construction. And then as we start looking at corrosion, so we know for a fact that the rate of carbonation of concrete has gone up substantially because of climate change. Temperature's up, CO2 in the atmosphere is up, and so that concrete's carbonating. And once that carbonation front reaches the steel, that protective passive layer breaks down and corrosion starts. And we know this. We know throughout the world we've got structures that 15 years ago we would say had 200 years of life. That lifespan has now dropped down to 50 years because we have now taken away that high pH. We're talking about pavements here, but we're really, if we're starting to look at sort of what we care about in our deterioration, we care about saturation, we care about the chlorides getting in there to steel. To pavement, if it's conventional, jointed, plain, doweled pavement, we don't care nearly as much. And then we definitely care about climate change-induced corrosion. So we're looking at ions in, we're looking at ions out. So we talk about de-icers, and we just had this discussion at breakfast. So if we think back to 30 or 40 years ago, the expectation was all of our pavements wouldn't be clean and dry after every single snow event, right? I mean, this is, now we want everything plowed, everything salted, everything clean. But 40 years ago, 30 years ago, when we put these pavements in, it was a very different regime. So we're starting to ask the pavements to do things they weren't originally intended to, and they're not performing as well. Well, it's not the pavement's fault, it is our fault. And trust me, I guarantee, I get lawyers calling every single week, at least one a week. Can you come consult on a slip and fall claim? Somebody did not plow a street, a sidewalk, and we fell down. This is major, big business. So we have de-icing salts, and then we have this new practice of anti-icing. So rather than throwing a rock salt down, we'll put some semi-saturated brines and we'll apply it dry. So this is one, there's sort of two sides of the house. Is this causing more deterioration or is this not? So there's lots of research going on. That's why we've got stuff up at Min Road. Turns out it might not be as big of a deal as we had thought. Actually, our old rock salt, when we do that, we actually get more deterioration than we get in a lot of our anti-icing. So that's one, just keep an eye on it. It's emerging trends. And then we talk of sort of the big bad nature of salts, and we've got lots of different salts available. We've got sodium chloride and magnesium chloride and calcium chloride and potassium acetate and potassium magnesium acetate and lots of different acronyms. But if we look around, in the most of the chemicals we're using are sodium chlorides. They are. So if we get samples from all over the Midwest, most of it is sodium chloride because it's cheap, it's relatively easy to use, and I've got kind of a ranking there, at least for concrete. Our mag chlorides are bad, and our calcium chlorides are slightly less bad, and our sodium chlorides are less bad from there. But our mag chlorides there, or calcium chlorides, we can get huge depression to freezing point. Huge depression to freezing point. Okay, so just talk through, now we're going to see a figure and we're going to see some chemistry, so we have now checked our list off, so we've done this. But the idea here is if I've got sodium chloride and that goes into my concrete, it's going to dissolve my calcium chloride, going to form sodium hydroxide, which then can form these deleterious products that are Friedel salts and delayed Ettringite. We can effectively de-aerotrain the concrete, so we can fill in the aerotrain pores with stuff that wasn't there originally. So there we go. We got fill in some stuff. So if we've got joint deterioration that shows up 8, 10, 12 years from now, you say, well, why did that happen? We can definitely take a look at that and see, have we de-aerotrained the concrete? If we've got calcium chloride, that calcium chloride can form what we'll call the boogeyman. The boogeyman is calcium oxychloride of various flavors. So if you're in the concrete world, this is something we've been spending a lot of time in the recent years looking at. And oxychloride is kind of scary because it is an expansive, transient mineral, but it forms between 40 and 50 degrees Fahrenheit. And actually, if it's really humid, you can get it to form in higher temperatures. And so I got lots of pictures on campus where we've got limestone where we've salted the crap out of the sidewalks. It soaks into the limestone, and then usually about the third week in July, the humidity's been up, and that limestone starts to fall apart because all this oxychloride is now forming in the middle of summer, and I'm getting de-icer salt attack in the summertime. Okay. We can crack this nut, but this is one, it exists. And then mag chloride, if we put that down, it'll actually convert our calcium silica hydrate into a magnesium silica hydrate, which is relatively porous, relatively weak, and then it kicks off a calcium chloride, and the calcium chloride then can form oxychloride. And so you can kind of step through your chemistry, but we've got to understand, we can't just randomly buy bags of crap from the side of the road and put it on. We have to understand the chemistry, we have to design for it. And so right now, this is where we'll say DOTs and designers, we've got designers designing things, and then we have the maintenance folks. They're probably not in the same building, they're probably not talking to each other, and they don't understand once we own it, maybe we shouldn't break our own stuff. Okay, so before we jump in here on sealers, we'll say sealers are like vitamins, okay? If you are inherently unhealthy, taking a load of vitamins does nothing except make expensive pee. Okay? So we've got a lot of folks sort of hawking wares, and if we're talking pavement preservation, but why should we throw good money after bad if it's not worth preserving? So step one, we want to make good concrete. And FHWA through the PEMS program, we're doing this all over the country. We know how to do this, but we need proper drainage. We can't let our joints sit there and be wet. We can't let our concrete sit there and be wet. We want to reduce the permeability of the concrete. We know how to do this. We know how to measure this. We've got very good techniques. But I always get lots of calls where, hey, my concrete's falling apart or my concrete's scaling. I said, okay, let's look at it. What are your specifications? Your specifications don't call out anything we actually care about. I don't care if it's 3,000, 4,000, 5,000 PSI. We have not failed a pavement because of low strength in the US in years and years and years. Say, except up at Minro, where we've done it on purpose. Or where you have somebody drive a dump truck across the sidewalk, and then I will say it's probably not the pavement's problem. It's we have treated it poorly. So reduce the permeability with low water to cement ratio and using SCMs or ACMs, and using well-graded aggregates and doing appropriate curing, making sure we have an adequate freeze-thaw or air void system in there. So not just saying, hey, 6% air. 6% air doesn't equal 6% air, doesn't equal 6% air. We know how to assess the air system. We've known this for a long, long time. And we want good practices for sawing and joint sealing. So with concrete, we will spend all this time with the design and the mixed design approvals and the approvals of materials, and we'll watch the construction process, and then the sun goes down and we get tired, so we go home, and then some 18-year-old kid is responsible for sawing in the middle of the night and hacks up all the joints. So we ought to make sure we might need to stay up overnight with the rest of the folks. Then once we've done all of these, then we can start talking about penetrating sealers. So first and foremost, we're not looking at bad concrete and then trying to fix concrete that maybe shouldn't be fixed. We're going to build it good from the beginning, and then we can talk about really long-term preservation methods to make it better for longer. Okay, so sealers. So when we talk about the field of penetrating sealers, it's a whole mishmash of language. And what I'm going to tell you is there is not a sealer on the market that can't be described. If the company can't describe it or won't describe it, they either don't know what's in it, or they do know what's in it and they don't want you to know. But either way, if that company cannot describe the mode of action, you probably don't want to spend a whole lot of time entertaining them. I can start a sealer company. We've got sealers all over in the lab, and they will vary from highly effective to colored water, because there's not a whole lot of standards, and so it is the Wild West. So what are we talking on sealers? So penetrating sealers, we'll kind of start up here to the upper left. We have what we call continuous films. And so this would be your acrylics. And so this is typically used for architectural preservation. We don't put a lot of acrylics on pavement because they tend to be slippery and they have low permeability and some issues with pH stability, so they tend to peel off. But we have continuous films, and if I put a sufficient number of solvents in them, I can get them to soak into my concrete, so we'll say they kind of penetrate. Then we have what we call our pore blocking products, and these mostly we'll say are some sort of fatty acid. So you can say effectively, I give you a stick of butter, we can go grind that stick of butter out on the sidewalk, and that sidewalk's going to be pretty waterproof. That fatty acid has got it in the pores, it's plugged it up, and it works pretty well. So we've got stearic acids, we've got linseed oil, we've got soybean oils, we've got soy methyl ester, we've got lots of different things that effectively just plug up the pores. Upper right here, we have hydrophobics or pore liners. So they get in there, and because they will chemically bond with the pores, some work better on early concrete, some on the later concrete, but they will water repel. So if you ever use Rain-X on your windshield, that's a siloxane molecule, causes it to bead up, it bonds with your windshield, and so you have pore liners. And then we kind of, on the lower right, that's a really thick coating, so think if we're doing bridge decks, that's epoxies. If I have enough solvent in there, it'll penetrate to a bit. But we're not putting epoxies down on pavements or pavement joints as a standard practice. So we're really looking at pore blockers and pore liners for the most part. And so I'll throw this up. And so you look at it and you say, oh, there's lots of different versions and lots of different functionalities. You don't need to memorize it. The answer is yes. Yes, but we understand them. There are truly not any magic juice out there. We can quantify and we can measure it. Okay, so how are we going to quantify this? So we're going to look at this. So many of them talk about hydrophobicity, and that's your water beading or your Thompson's water seal effect. And so we are using a chemical reaction to reduce the contact or the surface tension on the surface. And we can measure this. Nice thing about this is we can take a picture. I've got apps on my phone that give me a really good idea of our hydrophobicity. Okay, so what? Someone walks in my door. This is what happens to DOTs all the time, or youngster engineers. They walk in the door and I have a jug of something that is the greatest thing ever. Well, if it is, I don't really want to pass it up, but I've been sold magic beans before. So I want to know if it's real. Is it real or is it colored water? I want to know if the thing you say is in there is actually there. That's pretty important. I want to know in my concrete, after it's been in the field a while, is it still working? And I want to quantify it with mortal testing. And so I get this on a regular basis. Someone has done some oddball test at some far-flung university somewhere in the world. Northern Moldova has a test method that is the only test method in the world that accurately describes our product. You don't possess the skills or the technique to measure it. And you kind of go, really? Because I'm pretty smart, and I got a ton of really expensive stuff in the lab. And sort of my rules are, if I can't get to an answer really quickly, it's probably bullshit. And so when you're telling me I can't do it, then it's probably a challenge, and we're going to get all up in your business. And this is why many, many sealer companies don't talk to me anymore. So oftentimes you're going to get on a jug of sealer is it is NCHRP 244 approved. If you see, look at this. NCHRP 244 is a report. It's a report. That's like saying the moon is Encyclopedia M approved. Doesn't mean anything. There's information there. It's not a test method. It's not a certification. And so this is a lot of times come in and say, we're 244 approved. Well, number one, it's old. So I think this is early 80s, so the chemistry has changed, our ability to quantify. It's looking at bridge decks. It's good information, but it's not a test method. And so, all right, so once we get past that, and I've just told you that, I've broken all the hopes and dreams, so then what do we really want? Let's ask for the thing we want, let's measure the thing we want, let's move forward. So ideally, we want to reduce that water movement in. If I can keep a lower degree of saturation, I've got less freeze-thaw, I got less chlorides moving in, I got less material for actual reactions, whether that be oxychloride or etrangite or whatever else. So if we can keep water out, I don't really go to Arizona and talk about concrete durability issues very much. Just sort of sits there and looks at you. We want to reduce chloride movement in. So if I've got steel, yes, that's very important. If I don't have steel, it's all those other deleterious reaction products. So we want to keep that, if it's steel, we want to keep that critical chloride threshold low. But we also don't want to impede water movement out. If I seal the surface, in concrete floors, they figured this out many, many years ago. I can put down a super impermeable floor. Especially if it's on the ground, though, water is moving up through that concrete. It pools underneath that, and it tends to pop the coating, and now we've got slip and trip issues, and we've got lots of lawsuits. So we don't want to remove that water out. We would really like it to dry, so we don't have unintended freeze-thaw issues, and we don't want it to degrade too easily, and we'll talk about sort of reapplication or the purpose of reapplication here in a minute. But ideally, I don't want to put something down that sees UV light and then completely falls apart in 6 months. There's a lot of things that are not particularly UV stable. You ever try it, take a polyurethane that you might put on your flooring inside, coat some of your step or your sidewalk out front of your house. It will yellow and it will fall apart in about 6 months. So there's many different things that work well in one application but not another. All right, so hydrophobicity. So I'm going to talk, I've got lots of different sealers in here, and I'll kind of talk you through some of the families, but hydrophobicity is kind of an easy one. So we've got controls, we've got lithium silicates and colloidal silica, that's our LS or LC. So those are, we'll say they're sealers in that they go in, react with the calcium hydroxide, and they refine the pores. So they have insoluble reaction products that are left. We got silanes. So silanes are sort of our very common hydrophobic sealer. Silanes work best with young concrete because they're going to be bonding with that calcium hydroxide phase. We've got some pore blockers, some sterates, got an acrylic there, that's a thin sealer, and we've got a soy methyl ester. But key is, if I put a sealer down, I put a drop of water on it, I can use my phone or I can use a camera and I can see, is it hydrophobic? That doesn't mean everything, but that's a pretty cheap and easy way to see if it's still there. Does it work? Okay, so if we look at water movement in concrete, again, I like to do really low-cost stuff first. We like to look at absorption, so we take a sample of our concrete here, and we seal the sides of it, and we put it just in contact with water, and we let it wick up or soak up water with capillary action. Pretty cheap and easy. I can measure the mass of it, and if we kind of look here to the left, soaks up water. It's got kind of this nick point where we filled all the capillary pores, and then we start filling the entrained air. Cheap and easy. I can measure the mass, and it tells me about the pore system. Really easy. And so if it soaks up less, then there's less water in, it's going to be more durable. So pretty easy test. So if we look at this at real sealers, I'd say I can shoot this one easy. I can't hardly shoot that one very well. I'm at an angle. So, well, we could get that'd be too easy, right? That'd be too easy. All right, so we've got a control here, soaks up a lot of water, and then we've got various different sealers. We can quantify the reduction in moisture in. Don't need to necessarily talk about the different flavors there, other than here's kind of our silanes, and here's our siloxanes, and here's some of those other products. But we can look at water in. Awesome, works great. And then the thing with that is after I'm done testing, I can then saturate it, get it 100% saturated, and I can calculate my relationship or time to that critical saturation. So we know for concrete, once we get above 85% saturation, doesn't matter how much air is in there, once it freezes, it will blow up. We have to keep it below 85% saturation for any sort of durability. You can say, oh, here's a sample we did for Iowa that had a really marginal air system. So it would be susceptible to freeze-thaw. Here's one made with a decracking aggregate, and we can see what is that extension, time extension, to critical saturation. And it's substantial for both of them, but the shape of those curves is different because they are functioning differently. So the next part of that is they're not all the same. So I can't apply the same penetrating sealer in all situations to all concrete. So we have to understand what our concrete might be vulnerable to first. And so we take a look at that, and we can kind of do some projections and say, I mean, some of these things, you're looking at 6, 7, 8, 9 times extension to lifespan by applying a penetrating sealer. There's not a whole lot else I can do that's that effective. Okay. Other thing we look at is water in and then water out. So with this test, we're letting these samples soak water, then we flip them over, put them in the environmental chamber, and we let them dry out. And this is important because it's kind of simulates field conditions. But here we have our sample that does not have very good air system, so it's like 3% air. So if we got it in the field, we'd be kind of uneasy about it. Our control sucks up water, and then it gives it off. But our other sealers, they might not have sucked up as much, but they get back to about the same point. So we're looking at this, at least in the inadequate air sample, we've not impeded drying. Looks pretty good. Bottom here, that's our silane, our hydrophobic, so it doesn't soak up, and it doesn't have near as much water there at the end. And then if we look at our decracker, this is kind of interesting though. Our decracker soaks up comparatively a lot more water. We would expect that, higher porosity in the rock. But we have some sealers over here that actually impede drying. You say, oh, if I'm susceptible to freeze-thaw damage in my rock, I better not be holding the water in there. So maybe some of those pore blocking sealers might not be the appropriate ones for that situation if we have decracking susceptibility. So pore size and distribution matters. You can prevent drying. Then if we take those samples and we soak them so they're fully saturated, and then we dry them out, we can take a look at sort of time to delay for the various sealers. So ideally, they're not going to be completely saturated, but what happens if we have sort of a frozen ground rain event, our pavements then flooding in the wintertime, which we do get, we'll say Minnesota, Wisconsin, North Dakota. What happens if that thing gets completely saturated and then we have freezing? You start saying, well, some of these are absolutely going to delay that time to drying. Or if here's our inadequate air, here's our decracking, and so if that's a concern, maybe we want a sealer that actually actively helps it dry versus keeps the water in. All right, a couple more, and we'll try to get us back on here. Other thing we worry about is chloride penetration. So chloride penetration is pretty quick and easy too. We take a sample, we pond some chlorides on the surface, we mill down after it's ponded for 90 days, and we look at the chloride profile. ASTM, we do it lots of different depths. Our AASHTO, we just do it near the surface and deeper in the surface. So top 1/2 inch and then at about 1.5 inches. And so if we look at across sealers, here's our control right here, here's our control, the top and the bottom. We say, okay, all of our sealers at the top have prevented chloride ingress to some degree. Some, like our silanes here, prevented it. 50% of the chlorides going in. That's pretty good. That's our silanes applied in nice, clean, dry concrete. Here's our same silane applied to semi-damp concrete. It's not soaked in as well. It doesn't work as well. We can measure this. Again, not particularly expensive tests. Then we have our silanes and our siloxanes, which are, we'll say, bigger, sort of less sophisticated molecules to a silane. A little bit different chemistry, but it's similar, I'd say rather similar. Often marketed as salt guards. They are very good for sidewalks and driveways to keep de-icer scaling down. They don't actually prevent any salt from going in. It slips right by the molecules. So we can measure this. If this is of interest, we can definitely measure it. Then if we look at freeze-thaw, so freeze-thaw, this is our NCHRP test. So it's freezing and thawing one-dimensionally with only one side in contact with concrete, or with the freezing solution. So this is this is a version of a US version of a Rylum test that we use. And we can kind of look at, this is our sample with poor air, and we're looking at mass loss over time. Our sealers have done a very good job of extending that lifespan. Or if we look at our decracker, we have 2 of our sealers have done a really good job, but our pore blocker there actually made freeze-thaw durability worse because it didn't allow the water to get out, so it held it in. Then we can look at scaling. Scaling, again, is pretty cheap and easy, and it's nice and visual, so you say, oh, that looks better than that. Maybe I want to use this. Pretty easy. Then we can look at our boogie, kind of last thing here's our boogeyman, is that oxychloride formation. So our control kind of idea here is we take our concrete sample, we're going to expose it to a certain amount of calcium chloride, and then we run it through a low temperature scanning DSC, and we look at the actual formation of that crystal. And the key here is this is high, that's our control. Those are all our sealers, a lot less. And so if this is of concern, oxychloride's of concern, sealers are a pretty effective treatment to minimize oxychloride potential. Okay, so conclusions, recommendations. So there's a ton of different chemicals that exist that have lots of different modes of action. We've got to understand the modes of action to know what we expect out of our performance. They don't function along all the same pathways. Some are good applied to early concrete, some are good for later concrete, some are good for deteriorated concrete. Some, if I did that, I would actually make the deterioration worse. And that NCHRP 244 is a report. Doesn't mean anything. It is not a seal of approval. At a minimum, I can measure absorption and desorption cheaply and easily in the lab. I can understand the mechanisms. Okay, that's good. I can saturate them and measure desaturation, pretty cheap and easy. I can look at contact angle, cheap and easy. I can look at chloride penetration. Most DOT labs have the ability to do that, not particularly expensive. That should be the minimum. That's an easy smell test to do on anything, and I can do it on my concrete. We can look at corrosion initiation if we're looking at structures. We can look at one-dimensional freeze-thaw if we wanted to. We can look at oxychloride. Might be beneficial if these are of interest or not. Here's sort of the piece with reapplication, especially with pavement preservation. Reapplication is likely not needed in most situations. If I put my sealer on correctly during construction, or soon after construction, we've got somewhere between a 10 to 15 year life cycle for that sealer before we look at it and we don't know if it's still there. If our concrete is effectively 10 years old before it sees any real amounts of salt or water intrusion, it's pretty old. If I could wait to put my concrete in service for 10 years, our durability would be spectacular. We'd have Roman level concrete durability. And so at this point, if we need to reapply, we're probably going to have to do some grinding or milling of the surface. Because we've built up a nice schmutz layer of tire dirt, we've built up a carbonated layer, we might need to grind it so it can accept some sealers. But again, if the concrete's not worth preserving, let's not throw good money after bad. It's kind of the key. So there's a really good body of evidence supporting the use of penetrating sealers. It improves many different properties. So we can do this. We know it works. The value proposition's there, the technology's there, the test methods are there. We just have to use them. We just say, let's be healthy and then allow the vitamins to make us healthier. We know how to do that. Let's not sort of skip the design phase and then just be reactive with applying the sealers. Let's do both of them, and then we're all better for the long run. So I think everyone in the room will agree, we've got more work than we all collectively can handle, and so I don't need to go replace anything in my lifetime. There's going to be plenty of work, and so let's do it right, let's maintain it well, and then we can move on and use our money for something else. All right, with that, okay, we're appreciate it.
If there is a quick question, we have time.
Can we get the mic back here, please?
You can just repeat the question.
Yeah, so in the design and construction, we know what aggregates we used, we know what permeability we specified, we know what SEMs exist, and then we know how that was treated in its early life. If we and we're doing a pretty good job of quantifying that, so yes, I know this makes sense. I can also then at my later ages know that maybe a pore blocker is not appropriate, maybe it is appropriate. We probably wouldn't apply a pure silane at a later age. We'd stick to a siloxane. And so it's all going to be site-specific, but we understand enough about the concrete and the environment and its use case to make an informed decision. Yes?
What I'm trying to understand, you said that for 8 unique pavements, each one you could do the preservation as far as penetrating sealers for its life. That's pretty correct, right?
Correct.
Okay, so now let's go to a 10-year-old pavement that you showed, or 8 years old, or whatever. Can you go in knowing nothing about how it was built and then decide what you should do or shouldn't do on that?
Yes, and that's easy enough. We can easily take a core or look at a 10-year-old pavement and say, we run petrography, is this 10-year-old pavement functional? What's in it? What's the permeability? And make an informed decision. And what we can't get sort of distracted is if we look at every sealer on the market, then you say, how in the world am I supposed to pick? Because there's 900 sealers available. There's not. There's a few families of sealers, and we can kind of group preservation into the pavement and what we ultimately want in the end. Yes.
Thank you very much.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.